If we can please be seated, we'll make a start. So good evening, everyone, and welcome. I start by acknowledging and paying respect to the traditional owners of the land on which I am this evening, the Ngunnawal and Ngambri people. The Australian Academy of Science is built upon their ancestral lands, and as we share our knowledge, teaching, learning and research practices, may we also pay respect to the knowledge embedded within the Aboriginal custodianship of country. I am Ivan Marusik, Vice President and Secretary for Physical Sciences of the Australian Academy of Science, and I'm delighted to be here with you today for the 2024 Haddon Forrester King Medal and Lecture. I warmly welcome everyone here to the Shine Dome and those of you who are joining online. A few items before we get started. For those wishing to ask questions of Professor Cox, can you please do so at the conclusion of the lecture? There'll be an extensive Q&A session. And to those joining the conversation on Twitter, X, you can do so using a hashtag which is on the bottom of that screen, whatever that means. Now to the Haddon Forrester King Medal and Lecture. The award is sponsored by Rio Tinto and is one of the Academy's prestigious career awards for lifelong achievement and outstanding contribution to science. The award is made in honour of the contributions of the late Haddon Forrester King, whose work applied the geological and related scientists to the search for mineral deposits in Australia and elsewhere. The award is made to a scientist in Australia or overseas, recognising original and sustained contributions to earth sciences of particular relevance to mineral deposits. King was a prominent figure in this field. He became Director of Exploration for what was then Zinc Rio Tinto of Australia, known as CRA, in 1962. And he continued in this capacity until he retired in 1970. He remained on as a consultant at CRA until 1986. King lived and worked in various locations worldwide before he came to Broken Hill to become Chief Geologist at Consolidated Zinc and later Director of Exploration at CRA. He oversaw the discovery and development of vast mineral deposits in the Hamersley in Western Australia and the Panguna copper deposit on Bougainville. He also chaired the Bass-Becking Geobiological Laboratory, and like many other scientists, he continued to work as a consultant for many years after his official retirement. King recognised that Broken Hill ore and other deposits like it originated as sedimentary layers of metals rather than replacements from metallic solutions. This was a significant milestone in mining geology and strongly influenced the industry. The Academy is grateful also very much to the friends and family of Haddon King, who supported the establishment of this award after he passed away in 1990. I would like to give special welcome to Ted Johnston, who is Haddon King's son-in-law, and he has travelled from far to be with us here this evening. Welcome, Ted. We're also grateful for Rio Tinto's ongoing support, which allows the Academy to celebrate the work of great scientists with the Haddon Forrester King Medal. So before we get to Professor Cox's lecture, I'd like to welcome Graham Lilly to say a few words on behalf of Rio Tinto. So Graham, if you could please come forward.
Thank you, everybody. First of all, on behalf of Rio Tinto, and also, if I may, on behalf of the mineral exploration industry and the mining industry, heartily congratulate Professor Stephen Cox for the Haddon Forrester King Medal for 2024. And sincere thanks also to the Australian Academy of Sciences for this event hosted in this beautiful historic building. And also, if I would just acknowledge the family, the King family, for ongoing support and for establishing this medal with Rio Tinto in the 90s, if I'm 92. Thank you very much.
Thank you, Graham. It is now my great honour to present the 2024 Haddon Forrester King Medal to Emeritus Professor Stephen Cox. Let me just say a few words about Stephen. Professor Cox has conducted research spanning the fields of experimental rock deformation, field-based structural geology, microstructural analysis, isotope geochemistry, seismology and numerical simulation to explore how fluid migration deep in Earth's crust triggers earthquakes and generates the high permeabilities necessary to sustain development of many types of ore deposits whose formation involves large fluxes of metal-bearing fluids. I myself am a fluid mechanician, so I find this particularly fascinating. Stephen's research is providing a new understanding of the dynamic coupling between fluid flow, deformation processes and reaction involved in the formation of ore deposits. It also provides insight into how the structure of seismically active fault networks localises fluid migration pathways and ore deposit location at depth in Earth's crust. These new perspectives are critical to developing more effective strategies for exploring Earth's resources. Professor Cox has also demonstrated a consistent commitment to sharing his knowledge through his undergraduate teaching, training research students, and providing training courses for minerals industry geoscientists, both nationally and internationally. Congratulations, Stephen. I invite you to join me on stage. Please, now come. Oh, awesome. It's my job now to present the medal, which is actually quite heavy. It's a decent amount of ore. So now I invite Stephen to give his lecture titled, you can see the title there, Shock and Ore, Links Between Deep Crustal Fluid Migration, Earthquake Swarms and Ore Deposits. Stephen.
For the title of what I'm going to talk about today, I must give apology to the Bush administration for their adventures in the Gulf back in the early 90s, where they had a campaign called Shock and Ore. But the real title comes from Alan Good of Amira, who back in the early 2000s, when we were doing some work in Western Australia, said, you know, what you do is shock and awe, you know, earthquakes and ore deposits. So I thought I'd put that in today. I'm going to presage the talk by just a few thank yous, which are highly warranted. Firstly, to both Graham and Ivan. Thank you for the kind words and introduction. I also want to thank Rio Tinto and the King family, thank you Ted, for their ongoing support of this medal and the many opportunities it creates for awardees to communicate their research and the excitement and enthusiasm we have for the science we do. I entered research around about the mid-1970s when I started a PhD. That was well after Haddon King had retired from being Director of Exploration in the CRA group. But there's a kind of link because my research on gold deposits started in about 1982 when CRA Exploration, when I was at Monash, funded a short project to commence work on gold deposits in Central Victoria, namely around the Castlemaine, Chewton area of Central Victoria. And that really got me excited about how do these fault zones behave? Why is the gold there? What's the story? So that's really been with me for a long time, with many side journeys. The initial gold research was subsequently progressed by going to visit WMC Limited, Western Mining Corporation in Western Australia. They wanted me to give it a little bit of a course, and that led to a very protracted research activity with many, many honours students, a few PhD students, and was followed when Goldfields took over WMC's gold operations. And again, that area was the early stamping ground for Haddon Forrester King. He came over, I think, from Canada in 1934 to work with WMC and did a lot of work, especially around the Norseman area. I visited that, but I actually haven't worked on Norseman itself. So there's a kind of link, and he came here to work with who was then a very famous structural geologist, H.J.C. Connolly, whose work is not really recognised much these days, but was quite outstanding work. I particularly want to thank all those who were involved in the nomination, Ian, and all the people on the committee who reviewed and awarded the medal. I know many of the previous awardees of this medal since the early 1990s, and it's wonderful to see a couple of the previous awardees, or three of them here tonight, which is really nice for me. I feel very honoured to be included in your group, a cohort of quite amazing scientists and explorers, so it's a nice club to be in. Kira, wherever Kira is, Kira Scaife at the Academy, up the back there, she's very proficiently put together all the logistics needed to bring this thing to fruition tonight, so thank you, Kira. A career is not something that evolves in isolation. It's really the result of many people's activity. I've had very good fortune, particularly working initially at Monash, then at ANU, up to Newcastle, back to ANU, to work with a bunch of really neat people, wonderful scientists over the years. That's included numerous honours students, some outstanding graduate students, and some equally outstanding postdocs at various stages of their careers, and also more senior colleagues. In that vein, I want to highlight just a few names, in particular the impact of Mike Etheridge and Bruce Hobbs when I was at Monash, got me started on thinking about why do rocks form, what's going on, why do fluids flow through rocks. Then I came up here in 1984, I think it was, for ANU for the first time, and that's when Mervyn Patterson started a long period of mentoring me and introducing me to the art of experimental rock deformation and some very quantitative science. So I started taking those laboratory results into the field, trying to understand what those laboratory results tell us, then going back into the lab and doing more relevant experiments. So it lasted for a long time. And then also a big influence was across the ditch in New Zealand. Rick Simpson moved from California to Otago, and he has been one of the key people bringing seismology into structural geology and getting us to think about faults as how they behave seismically. So he's done a lot of things and repeatedly harassed me with questions like, what magnitude earthquakes have produced this fault? And it's really only now that I'm starting to answer some of those questions that Rick posed many, many years ago, and frequently with great perception. Before I finish, I want to particularly acknowledge the role of the Research School of Earth Sciences in my career. It provides an outstanding, exceptional environment that encourages cross-disciplinary research, and from that I've benefited greatly because I like to talk with geologists, geochemists, geophysicists, and blending those things together has produced some of the things I'm going to talk about tonight. And the school really has allowed a lot of people to develop a very distinctive brand of science which doesn't sort of copy what everyone else is doing, bringing new things into the field. I also thank my wife Elizabeth up the back and the rest of the family. Elizabeth's support has sustained me and encouraged me over nearly 50 years or so, a journey that started as a newly graduated geologist working in regional mapping in the Geological Survey of Tasmania, to a researcher who now enjoys, in his retirement, something that feels like a superannuation-funded postdoc. So it's kind of nice to be a postdoc again, but the pace of work is much less than it was originally. Finally, before we move on, I want to thank all of you who have come tonight, and that includes those on the live stream. It's very, very amazing for me to have all you people come here. So thank you for coming and adding to the enjoyment of this celebration. Thank you very much. Right, now I need to sing for my supper a little bit. Not literally, it's all right, don't run away. So we're going to talk about links between deep crustal fluid circulation, earthquakes and ore deposits. There are three things I want to do tonight, and we'll go through them sequentially, and for those who aren't deeply into what I think about a lot, we'll have some explanations on the way and some minor tutorials. But firstly, what I want to do is outline some of the key characteristics of ore deposits, which form from a flux of, high volume flux of hot reactive fluids through these fluid pressurised and active fault zones, which are actively producing earthquakes. Once I've outlined what these things look like, and I'll focus largely on a class of deposits called orogenic gold deposits, because that's what I've worked on a bit, we'll present some examples of contemporary injection-driven earthquakes. And these, I think, provide an amazing analogue for the formation of ore deposits in fluid pressurised faults. Up till recently, we just thought, yes, they're seismically active structures which control where these loads are. But when some deep injection experiments started being done at depths of 4, 5, 6 kilometres, where fluids were pumped in, I started seeing a distinctive behaviour, which I think applies to all high fluid flux systems. So we'll talk about some engineered deep injection experiments, just one initially from northern South Australia. Then I'll take you on a little tour through several examples of natural injection-driven seismicity. And finally, we'll try and bring that together a little bit to explore how this injection-driven seismicity provides some new insights about some of the physical processes associated with ore formation in active fluid pressurised faults. Okay, some terminology. My field is redolent with all sorts of jargon, so we will need to understand a few things. Here, there's 3 boxes. Here we go. Get this mouse to work. There we go. So this is a schematic section down through the Earth's crust from surface at naught down to 35 kilometres or so. And we're talking here schematically about what we call the permeability, the ability of rock to have fluids flow through it. So in the near surface environment, down to maybe 3 or 4 kilometres, depending on where you are, the rocks are high permeability. That is, fluids can migrate through them easily. Rainwater, groundwater gets into them, moves through them. But as we go deeper, the confining pressure gets higher and the temperature gets higher, and that closes the cracks and pores in rocks. And so permeability becomes very, very low, and it gets very hard to get fluids to go through these rocks. So up in that high permeability regime here, the fluid pressure with depth varies as a function of the density of the fluid. It's simply the fluid pressure is density of the fluid times gravitational acceleration times depth z. And it's essentially a linear relationship approximately. And if that continued down into the deeper crust, it would form what we call a hydrostatic regime or a near hydrostatic regime. But that'll only occur when we're in a part of the crust which is relatively inactive and there are no fluids being generated. There's no fluid production from, say, magmas which are crystallising, expelling fluids, or there's no cooking of the lower crust or prograde metamorphism, which is letting fluids evolve from rocks as they dehydrate and decarbonate. When we've got active fluid production, we go from this undrained condition into this regime over here where the fluid pressure at depth, particularly in active fault zones which are localising flow of fluids out through the Earth, we go from the hydrostatic regime or the near hydrostatic regime into what we call an overpressured regime. And it can't increase infinitely, it's limited basically by the density of rock. So the maximum pressure is approximately, it varies a little bit, density of rock times G times depth again. And that's about 60% higher than hydrostatic. We're going to talk a lot about what's going on in this overpressured regime where we're generating fluids at certain times in Earth's history in certain places of the Earth. The other thing I want to explain for those who aren't aficionados is how we discuss forces in the Earth. We talk about stress, which is force per unit area, and anywhere inside the Earth we can resolve all the forces or stresses into 3 mutually perpendicular ones, just labelled sigma 1, sigma 2, sigma 3 for abbreviation. The important point I want to bring out here is it's this difference between the maximum stress and the minimum principal stress, sigma 1 minus sigma 3, which is what is thought mostly to drive deformation. It's called the stress difference, or in some textbooks, differential stress. So I'll talk about differential stress a little bit as we go through. Okay, what are the fault-related ore deposits which form in these high fluid flux overpressured regimes in the Earth? The key one that I deal with a lot are orogenic gold deposits. The major producers of gold, for example, historically in Victoria, the gold production is orogenic gold deposits. In Western Australia and similar old Archean terrains in Canada, Zimbabwe, India, parts of Brazil, there are lots of these gold deposits. And the cartoon over here is borrowed from some of Groves and Goldfarb's work, which schematically shows some aspects which are thought to be relevant. So here we have, in yellow, a big crustal scale fault zone, which is allowing fluids to drain from the deep earth. It's very schematic and may be wrong in some aspects. Importantly, many of the deposits, if I can find the arrow, here we go, it's very badly behaved. Many of the deposits, such as this one up here, a gold, arsenic, tellurium, tungsten deposit, they form not on the big crustal scale structures. They form on tiny little ones, and I'll focus on these tiny little ones. Faults which may only be a kilometre long, a kilometre deep. They're not going to produce big earthquakes, whereas these big crustal scale things might localise the magnitude 6s and 7s. Okay? The fluids are of various sources. They might come from deeper in the mantle, from downgoing subducting oceanic plates, which are devolatilizing as they heat up. They could be from metamorphic fluids as the lower crust gets cooked in these plate collision zones. We might be producing some of those. Some people argue that there may be a contribution from magmatic bodies, granitoid materials which form by melting in the deep crust. Maybe, maybe not. Anyway, that's the structure. By the way, Groves and Sillitoe are early recipients of the Haddon Forrester King, so I just want to note that. There are other deposits, the iron oxide copper gold deposits, which are quite abundant in Australia. The really biggest one on the planet is Olympic Dam in South Australia, but there are many up in the Cloncurry area, and in many other continents there are these iron oxide copper gold deposits, which sometimes are resources of uranium and rare earth elements, such as Olympic Dam. The ones in Cloncurry are very strongly related to faults or their deeper, more ductile equivalent shear zones, and even the big deposits like Olympic Dam, which are massive breccia, broken rock complexes, they probably have feeder systems underneath which are fault controlled, so faults are probably active. The other class of deposits which often have a strong component of fault-related control of the fluid flow and localisation of ore deposits are what we call intrusion-related deposits, such as the large porphyry copper, sometimes molybdenum deposits, which occur around the Pacific Rim and in various other areas which are our major copper resource globally. They are dominated by lots of little veins or mineral-sealed fractures, but often, particularly in the distal parts of these systems, are very strongly fault controlled. Related to those, in the higher level up here, we have a class of gold-silver deposits which are called high to intermediate sulphidation epithermals. I won't talk much about them because Dick Henley's here and he knows a darn sight more about those than I do. There are also granite-related tin, tungsten, copper ore bodies and various types of gold deposits related to intrusions, and one example I worked on years ago is the Porgera deposit, which is an amazingly rich, or was an amazingly rich deposit in the highlands of PNG. I'm going to focus largely on the so-called orogenic gold deposits. So what are the key features of these deposit classes? Importantly, they form in and around faults while they're active, and I'll show you some of the evidence to show you that. It looks like they form at various depths in the crust, not in the near surface, but at depths ranging from about 5 kilometres to as deep as 20 kilometres or so, in temperatures which range from around about 250 degrees up to as high as 450 degrees. They don't seem to form at much higher temperatures. Some people have argued maybe they do, but maybe they don't. The fluids we know a lot about because the fluids are captured in crystals of quartz, for example. When the quartz grows in these mineralised fluid systems, we can have something like this one over here, which is a little capsule of fluid which has been captured as the quartz crystal grew about, in this case, 420 million years ago. So we're looking at fluid which was captured in this quartz 420 million years ago. And we can look at it in the microscope or use something like a Raman spectrometer and work out what's going on here. So we know that most of the image here is quartz, but here's our liquid water, and we can freeze that and work out what its salinity is, and usually the salinity is very low, 5 or 8% or so. This is liquid carbon dioxide, and then we can take a Raman spectrometer into the middle here, and that is a vapour bubble which is made of carbon dioxide and methane. We'll come back to carbon dioxide later in the lecture because a lot of it's pouring out of the Earth's crust into the atmosphere as we speak. So the fluids are H2O, CO2, methane, sometimes a bit of hydrogen sulfide, sometimes a bit of nitrogen, and they're typically quite low salinity, presumably derived from prograde metamorphism of deep metamorphic systems, either in subducting slabs or the deep crust. Characteristically, there's intensive fluid rock reaction around these fault zones. The host rocks around the faults have their composition changed by reacting with the fluid, and these changes can be very severe, turning a dolerite, for example, into a quartz carbonate microrock, quite a massive change in chemistry. Often it's a lot of addition of water, carbon dioxide, a lot of sulphur as sulfide minerals. Potassium produces things like micas, so this is very common. And depletion, of course, in other elements such as calcium and many other elements. The gold grades are very variable. Unfortunately, a lot of deposits have really low grades. We're talking less than 1 gram per tonne, not mineable. But commonly, particularly in places like Central Victorian goldfields, grades can be as high as 30 grams per tonne or 1 ounce per tonne or so. The example on the right here is from the Fosterville gold deposit, which is about 25 kilometres east of Bendigo. It's actively mined now. We're looking at a vein of quartz with some dark bands in it, which have various minerals in it, but all these yellow spots are gold, and it's very, very rare to see gold like that in one of these deposits. Usually at several grams per tonne, you can't see the gold. It gets extracted by fantastic metallurgy. But this one's running about 1 kilogram per tonne of gold, which is quite amazing. There's not a lot of that there, but it's made a very rich deposit. The gold, as we'll see in a minute, can occur both within these veins, which are fractures, which have opened up and been sealed by growth of minerals, or in some cases it forms in a strongly altered rock around the fault zone. So the fluids have migrated out of the fault, reacted with the rock, and chemical reactions have scavenged the gold out, as well as other minerals. Importantly, we'll look later at quantifying this, but these are large fluid flow regimes. And by large, I'm talking about Sydney Harbour type volumes. Sydney Harbour is about half a cubic kilometre of fluid, and many of these deposits require at least that, if not several Sydney Harbours to make them work. So we're talking about getting large volumes of fluid through really small volumes of the crust, and that's a key issue that explorationists need to address. What do the deposits look like? Okay, we've said they form in and around faults, but they form typically in what we call dilatant fault segments, where the faults have actually opened up a little bit. And here's an example from my very early work at Wattle Gully down near Castlemaine, where there's a fault cutting across these blue folded sedimentary rocks. They're sandstones and slates, and there's a fault zone cutting across, and there's a steep fault there, and off the side of the diagram, the fault goes steep down here again. And as the fault's moved on that non-planar fault, it's actually opened up space. And where we open up space, we create permeability. And that's allowed those gold fluids to localise and flow through that zone. And if the chemistry is right by reaction with the wall rock, that's where the gold gets deposited. So we have these two classes of veins of quartz-filled dilatant fractures. There are shear fractures or faults. They're actually filling the fault slip zone itself. And then off to the side, as we see down here, macroscopically there are often these extension fractures which have opened up just like that. They're not faults, they're just popping open. We'll see later that we call them hydrofractures, and we come across that term a lot these days. They are also quartz-filled because fluids flow through there and deposited gold within them. Mostly these class of deposits are formed in very small, low displacement faults. So typically the net slip, displacement of strata, or geological boundaries in there, is less than 100 metres. The Wattle Gully one is about 40 to 50 metres at most. And the fault lengths are really quite small. They're only 1,000 metres to maybe 2,000 metres at most, commonly less than 1,000 metres. You can't produce a magnitude 6 earthquake in a 1,000 metre long fault. The biggest you can produce, as we'll see later, is a magnitude 4 earthquake. We'll explore that later in the lecture. Significantly also, these deposits are hosted predominantly within reverse faults, that is, faults which are moving when we're horizontally shortening the crust. If we squeeze the crust like that, we need to shorten it, and so these faults allow that shortening to occur. They also occur in strike-slip fault regimes where rock slabs are moving nearly horizontally past each other. They're much less common in environments where the crust is stretching horizontally, but there are some examples. Okay, in detail, what do they look like? If we go down to the scale of an underground opening, here's an example from St Ives Goldfield in Western Australia. We see here a lot of action going on. The dark material is a very old Archean basalt. It's about 2.7 billion years old. And the white stuff are quartz veins. So we have this one through here is a dilatant fault. So the fault has slipped as shown by the arrows, and it's also opened up. And similarly underneath that there's another fault. But coming out of it we see these wedge-shaped quartz veins. They are the extension veins which commonly occur adjacent to these lodes. And you'll see some of them are nicely growing off this structure, others cut across the lodes. And what we see when we look at this in detail is mutually overprinting relationships. There's extension fractures, there's slip events, there's extension fractures overprint those, slip events overprint those, so there's quite a nice story in there. On the right-hand side, we're back to Wattle Gully in Victoria. This is a very small scale example. Notice the scale in the bottom left, only 10 centimetres. This is the very end of a lode which was mined underground, and here it's just petering out, but again we can see the very nice extension fractures off to the side. The wall rocks are slate, and there's not much quartz along the fault there, but we can use the geometry of the veins in here to infer that the top block has moved up and the bottom block has moved down. Zooming in a bit further, we often see very complex structures inside these so-called fault-fill veins. So here we see what we call a laminated texture, many, many different textural zones. And if you zoom in at the thin section scale under the microscope, each of these zones commonly has very fine internal structures. So basically, these sorts of fault-fill veins are recording numerous episodes of slip, dilation, opening, breaking of rocks, which we call brecciation, and then mineral deposition sealed them again. So doing this hundreds, if not thousands of times. And the faults from these textures we see above, we see the faults reseal. So the minerals depositing from the fluid glue the fault back together and give it cohesive strength before the next episode of slip occurs. What we don't see in here, and this contrasts with regular faults out there that produce earthquakes mostly, is there's minimal development of what we call frictional wear materials. That is materials which are produced by grinding of the rock and crushing it up, abrasive wear, like running sandpaper over a piece of wood. We very rarely see much development of that in these systems, so they're dominantly dilatant structures rather than frictional wear structures. On the right we have a nice example of a structure where we've got a fault here. It steps across a big opening there and goes up there. It's a structure we call a dilatant jog. Where the fault deflects allows a large opening. And where we have those preferentially large openings is where most of the fluid flows, because that's where the permeability is. Importantly, and notice the scale, we've got over 1 metre of displacement in there because we can match this corner with that corner up there. That can't occur in one event. This fault's only a few hundred metres long. It's thousands and thousands of slip events, which we'll come back to later on. If we zoom into extension veins, we see really nice evidence for thousands of episodes of opening or dilation, then sealing by deposition of minerals. This is a nice, nearly horizontal extension vein from a lovely deposit in Quebec called the Sigma mine in Val d'Or. And the white is quartz and the black is a boron silicate mineral called tourmaline. And so while this vein's been opening, it's been growing quartz and tourmaline. And there's also about 120 grams per tonne of gold in that vein, which is quite nice. If we take a thin section in an area like that, we see what we have down below here, this amazing finely banded structures. And these are vein growth structures we call crack seal inclusion bands. And they've been peeled off the vein wall at every opening event. Little tourmaline needles have grown, as on the right, but quartz has swamped them and glued the whole thing back together. And to do this and produce that vein, we probably need about 10,000 of these crack seal increments to produce this vein, which is nearly 1 metre wide. So thousands and thousands of opening and sealing events. We'll see later, we're dealing with fluid pressurisation, cracking, what we call hydrofracking, bad name these days, but there it is, it's naturally occurring. Another example, this is not from a gold deposit, this is just up the road in Lake Burrinjuck where there's an amazing limestone sequence. And there's a vein system which is everything like Bendigo is, except it's just all calcite. There's no gold, bit of fluorite, nothing else. But here we see a vein within a fault, and we see these horizontal structures are slip surfaces, and there are little bands in here which are, again, these crack seal inclusion bands, are little slivers of wall rock which has been peeled off at every slip event. And these are important because they tell us about the size of the slip events. In these cases, if we measure parallel to the slip surfaces that are opening here, we're dealing with maybe several tens of microns, a few hundred microns, and in some cases up to a millimetre or two. They're very, very small slip events which are producing these structures. So the point then is that the net slip, or the total slip in this fault, occurs by many, many thousands, in fact tens of thousands of slip events. Okay, what are the fluid pressure regimes and stress regimes? Remember I talked earlier about fluid pressure and stress? Well, there's a diagram I don't want you to get too worried about, but on the bottom line, we're measuring this parameter differential stress, which is commonly the driver of crustal deformation. And on the vertical axis is a measure of the fluid pressure. It's a parameter we call the pore fluid factor, which is how high is the fluid pressure, PF, relative to the vertical stress. And if it's 1, we talk about lithostatic pressure. Okay? That's nearly the limit that we can build up fluid pressure inside the Earth. What we find is if we have a system which has got these dilatant fault fill veins and the lateral hydrofrac extension veins, they tell us a lot about stress state. For example, these hydrofrac veins here, the extension ones, can only form in this red regime up here. Fluid pressure is a little bit above lithostatic, and notice the stress differences or differential stresses are very low, less than 4 times the tensile strength of rock. So say less than about 40 megapascals or so. That's quite low stresses. So a lot of these systems form up here, and if we get into the blue bit there, if we touch it there, then the fault fails in that regime there. All the stress and fluid pressure states below that coloured line are stable. The rock is just elastically deformed, but as soon as we touch that line, bang, it fails, either in extension at low differential stress or by shear failure, a fault slip event, possibly seismogenic, at that higher differential stress. Okay, summarising what we've seen so far, we've got these deposits, not just orogenic gold, but many other intrusion-related deposits and even the iron oxide copper golds, form in vein-rich dilatant fault segments. There's minimal development of these frictional wear products, the breccias, the cataclasites, those sorts of things. In that they differ from most faults. If you go out into the Brindabellas and wander through the granites, you'll see faults all over the place. They're full of these wear materials. There are cataclasites, finely ground up rock. There are breccias, bigger fragments of rock in a cement matrix. There are even frictional melts out there produced by fast seismic slip under high pressure regimes at low fluid pressure. So these ore deposits are forming in quite special regimes. Low differential stresses, near lithostatic fluid pressures. So fluid flow and reaction then has occurred while the faults were active. You don't pump fluid through a fault after it's dead. You can only do it if the fault's actively slipping. You've got to keep regenerating that permeability all the time. If the fault is dead, you're never going to get anything through it. So it's important that they're active structures. The brittle failure processes transiently increase the permeability because we know from the observations that the fluids that are circulating through the fractures rapidly seal those fractures up again. They're just dumping silica, sometimes carbonates, a little bit of gold if you're lucky. So you've got this rapid fracture sealing which destroys the permeability, seals the thing off again, then we need to build up fluid pressure again to have another failure event. So this sustained fluid flow, importantly, requires the fault is repeatedly activated to repeatedly regenerate that permeability which gets destroyed by mineral deposition. Okay, that's the first bit. Now we're going to move on to the more seismological aspects of what I want to talk about. So a bit of background for those who aren't familiar with earthquakes and so forth. Slip-on faults is one of the major ways in which we can deform the Earth's crust, okay? We slip when we build up enough stress or fluid pressure. And just for eye candy, on the right I've got an aerial picture of the San Andreas Fault in California. Its western side is moving north, so that's the Pacific plate moving north, and the North American plate is effectively moving south relative to that at several centimetres per year. And as it's moving, that's building up the stress in the rock. And at the moment, the stress equals the strength of that fault, bang, that's when we have an earthquake form, okay? Another neat example over here is from around Wellington in the southern part of the North Island of New Zealand. Wellington's down here in the harbour, there's the harbour, and look at this amazing scarp going up through there. That's the Wellington Fault, which is an active structure. It hasn't slipped in recorded history, but it's a very young feature, and it goes right underneath New Zealand's Parliament House, through the city of Wellington down there, and through Lower Hutt up there. But there's a bigger fault over here called the Wairarapa Fault. Oh, the arrows have moved a bit. This structure failed in 1855 in what's thought to be a magnitude 8.2 earthquake. That's a really big earthquake. The slip was 20 metres. Imagine you're standing here now and a rupture goes through here. You would experience 20 metres offset in less than half a minute. Bang, dramatic structures. We're going to talk about structures which are much, much smaller than that. So here I've pinched a diagram from some of Rick Simpson's early work. If we look through a cross-section of the Earth's crust, we have the cool, strong, brittle upper crust, which goes down to about 15 or 20 kilometres or so. And below that, the pressures, the confining pressures, are so high, and the temperatures become higher as we go deeper, that inhibits failure, brittle failure. So deep in the crust, the so-called lower crust, the Earth is deforming viscously or plastically. So we don't produce much in the way of earthquakes. There are occasional ones down there. But the seismicity, all the interesting action, tends to occur in the upper 10 to 15 kilometres of the Earth's crust. And so you might have a big earthquake, it might nucleate there at that blue star, then it might rupture at something near the speed of sound, 2,000 or 3,000 metres per second, rupture tip propagation, produce a really big earthquake that may even rupture the Earth's surface. That earthquake then changes the stress state. It relieves the stress state around that rupture plane or rupture surface. So there's often a stress concentration around the perimeters, and so you have all these subsequent earthquakes come off down here, the darker blue ones. They're what we call aftershocks. They're a response to the changed stress state of the main shock. We might have a smaller one over here that nucleates at depth, like the 1989 Newcastle earthquake, was magnitude 5.6, doesn't get anywhere near the Earth's surface because it's a small rupture. There can be background micro-seismicity, the snap, crackle and pop that goes off just as little fractures slip, just to relieve a little bit of local shear stress. And there are segments in features such as the San Andreas fault, where the faults are creeping. There's really low level snap, crackle, pop, but there's also aseismic shear going on, not producing earthquakes. But the phenomenon we're going to talk a lot about for the rest of the lecture are what are called earthquake swarms. They occur in quite restricted domains, often unusually hot domains or domains where fluids pouring out of the Earth's crust. So we'll get into that a little bit more later on. So there are these two seismicity styles, by and large. There's a spectrum between them, of course. So we have these so-called main shock-aftershock sequences where you have the biggest rupture early in the sequence. There might be some foreshocks, might not be, but you don't know they're foreshocks till you've had the main shock sequence. And then you have the aftershock sequence in response to that changed stress of the big rupture. What we see is the largest of those aftershocks is usually about an order of magnitude less, 1 unit less magnitude than the main shock. We also notice here graphically showing that as the magnitude of the earthquakes is smaller, there's more of them, aren't there? They get more and more. We'll come back to that. That differs from earthquake swarms, which we're going to talk a lot about. In this case, there's no main shock, no large shock early in the sequence. It can be anywhere in the sequence. And we'll see that these things are typically quite small earthquakes, less than magnitude 4. There are some exceptions, of course, but again, we see increasing abundance of earthquakes the lower the magnitude in any area. And these swarms might last for anything from a few days to a few weeks. In some cases, there are long duration swarms which last for several years. One example, which is in the news a lot in the recent year, is all the volcanic activity in Iceland. That's producing amazing swarm sequences, and that magma chamber is currently inflating and it's getting ready to fail again. You can see the seismicity leading up to that inflation. But we'll talk about swarms which are not produced by magma migration, but by migration of aqueous and carbonic fluids. Another bit of the tutorial in seismology is there are really nice relationships between various earthquake parameters, such as the size of the rupture, the amount of energy release, which we call the seismic moment, and the moment magnitude, which is a logarithmic measure of that energy release, And of course, as we slip, we relieve a bit of stress, so the stress drop, and a response of that slip is an amount of slip. Don't take in too many details in this diagram, but we're plotting the moment magnitude up there, the logarithmic measure of magnitude, so 8's right up here, and we go down to even negative numbers, okay, because it's logarithmic. Just focus on this one here, a fault rupture, which is 1,000 metres long. The length of that Wattle Gully gold deposit and many other gold deposits. If we go up to the lines up here, typically the stress drops we have are a few megapascals. That gives us a magnitude 4 earthquake. And also, by the way, the displacement is the order of a couple of centimetres or so. Go down to a smaller rupture, a magnitude 0 rupture, which is really quite small. That's coming off a fault which has a rupture diameter of about 10 metres. And the slip again is of the order of a few fractions of a millimetre. So that gives you a scale. So we'll sit in my subsequent discussion in this realm in here. The other important point, of course, is this, what's called the Gutenberg-Richter frequency-magnitude relationship. Don't worry about the mathematics, but essentially it says if we have 1 magnitude 4 earthquake over here, there'll be 10 magnitude 3s, 100 magnitude 2s, 1,000 magnitude 1s, 10,000 magnitude 0s and so forth. There's a scaling relationship like that. The slope of this curve varies a bit, but it's typically about 1 plus or minus 0.2, 0.3 or so. So just keep in mind that the smaller the earthquakes, the more there are, and that occurs in both main shock-aftershock sequences as well as in the swarm sequences I'm going to talk about. Okay, so we can think in terms of what's driving the failure. So here's our little failure mode diagram again. Here's our failure envelope, the coloured line up there. And any stress and fluid pressure state under that, the rock is not deforming except elastically. Normal earthquakes, regular earthquakes, are driven largely by tectonic loading. That is, the plates, tectonic plates are moving relative to each other. As they move, they change the stress state. And on this diagram, we might start over here at a pore fluid factor of 0.4, nearly hydrostatic. As we grind the plates together, we'll drive the stress difference towards the right. And as soon as it touches that failure envelope, the blue line, that's when we generate an earthquake. That's what we call stress-driven failure or failure by tectonic loading. Okay? But we're dealing in a high fluid flux fault regime, or producing regime if you're lucky. And in that situation, fluid pressures can change on timescales much, much faster than the timescales at which tectonic loading occurs. So if we're at low differential stress, we can just pressurise the fault system by injecting fluid into it, and at this point here, we're going to produce an extension fracture. Some of those things we've seen next to the faults. Eventually, as we continue with that system, it'll migrate along there, and at that point where we get to that blue line, that's when we'll have a little earthquake slip event. Similarly, if we had a high differential stress, we might just fluid pressurise up to the blue line there, and then we'll just have an earthquake slip event, no veins. So the stress level, whether we're down at low stress or high stress, will control the style of the ore system. Is it dominated by faults, or is it dominated by extension veins, or is it a mixture of both veins and faults? And that's kind of neat. So we can talk then in terms of stress-driven failure, which is probably producing most main shock-aftershock sequences, or fluid pressurisation paths where we go up path C or B, and that's what we're going to call injection-driven failure, or if you're doing it in an engineered situation where you're injecting fluid at depth to either recover hydrocarbons or do something else underground, we call that injection-driven failure or hydrofracture or hydroshear, okay? Okay, so now we're going to look at some examples of injection-driven seismicity. And firstly, we'll look at one deep engineered injection experiment, which was conducted in northern South Australia in the Cooper Basin. It's called Habanero 4. They like using chilly names for these hot rock experiments. There they were trying to understand how to mine deep earth heat in a very hot radiogenic granite. The experiment failed in the end, and we might address that at the end. But I'll also show you some really neat examples of modern, contemporary, natural injection-driven seismicity, which is happening in various places around our planet. Okay, the Cooper Basin experiment, there were several experiments in the early 2000s, but I'll show you the nice data from the one in 2012. It was called Habanero 4. They drilled there to a depth of over 4,000 metres. A lot of taxpayers as well as investors' money was sunk into that hole. It was drilled below a sedimentary basin, several kilometres thick, into a high heat-producing uranium thorium-rich granite. The ambient temperature down there was 250 degrees. Over a period of 16 or so days, they injected 34,000 cubic metres of fluid at rates up to 60 litres per second. Now, to get some handle on that, 50 to 60 litres per second is around about 200 tonnes per hour of fluid being injected into this structure. And that has an effect. It's forcing the rock to fail, okay, and it fails seismically. The seismic array in there detected over 20,000 usable events, but notice the magnitudes between 3.1, really quite small events, and down to minus 0.3. They were controlling the pore pressure. It was 0.84 of lithostatic. Not high enough for extension fractures to form, but certainly in this high stress regime, enough to make that fault slip. And it's slipping in a crustal shortening regime, so it's a thrust fault where the top moves up relative to the underlying one. There are some nice data over here. They've mapped the flow rate with time, the wellhead pressure, and notice how the seismicity rate, that's the number of earthquakes per day, follows very nicely the injection rate. What does it look like? Here I've plotted the magnitude of the earthquakes as a function of time. There was initial injection, then they had some engineering problems, they stopped it, so the seismicity went up, went down, went up, went down again. Then they had a big break while they sorted out the problem, then they started routinely injecting. The biggest event is 3.1 over here, okay? The rupture diameters are typically between about 400 metres or so, assuming a stress drop of a few megapascals, down to the minus 0.3 is about a 6 metre diameter rupture. And here's a map of that. It's a fairly gently lying structure. It's dipping gently towards the west at about 10 degrees or so. And here's the maximum principal stress, the major stress acting on these rocks, roughly east-west. Injection was here roughly in that area there. And the red colours are the early events, thousands of them. But you see with time, as shown in the diagram over here, the seismicity migrates outwards. It's not migrating out in a regular way necessarily, it's migrating to the north much faster than it is to the south and much faster than it is to the east. Sorry, the west. It's hardly migrating at all to the east, and it appears like there might be some sort of barrier, like another fault or something like that, which is blocking the propagation of those ruptures. Anyway, the message here is that fluid injection at high pressures generates migratory swarm activity. Here we see the injection profile, so 34,000 cubic metres injected over 16.5 days. Here's the energy release, the so-called moment release. It maps the injection volume quite nicely. Injection stopped over here at 16.5 days. And here we see the migration just on a north-south transect. So you see initial migration with initial 2 pumping attempts, then they stopped pumping. When they resumed pumping, it took off, and you see the nice northerly migration. Here it's stalled for a while. There's some sort of barrier stopping the rupture propagation, but as they kept pumping, the fluid pressure eventually overcame that barrier, then shot up there and migrated away. Notice it keeps migrating a little bit after shut-off, but it does slow down substantially. We can look at that migration in terms of radial distance from that injection point, and that's shown very nicely here, and see a very nice front to the seismicity with a few blips coming out of it. Here's the stalling point, and then it takes off again up there. There's some nice mathematics which allows us to get some parameters. One is the hydraulic diffusivity, and we're doing a lot of work on that at the moment. And there seems to be a nice relationship that this hydraulic diffusivity gets higher the rate of pumping into these structures. That's different because accepted wisdom is this diffusivity relates to the permeability of the rock. It doesn't, actually relates to the volume of fluid you're injecting at what rate. Anyway, the seismicity front is the fluid migration front where we're grossly enhancing the permeability, perhaps by a factor of 10 to the 2 to 10 to the 4 at that seismicity front as ruptures propagate through. Down here we also see, after cut-off of the injection, seismicity starts getting less frequent, so we have essentially a trailing edge to seismicity. It's a bit diffuse, but that helps us understand in natural systems when the fluid injection is stopped. So this is an engineered one, but we need to understand nature. If we look more closely at this radial distance plot as a function of time, you can see there's a lot of very short burst-like activity, these vertical lines in here, which can contain anything from just a few earthquakes, micro-earthquakes really, up to this example I've brought out, which has got over 240 events. This burst of activity, which are called short migratory bursts, occur over durations of a few hours at most. The diameter of the rupture area is usually measured by a few hundreds of metres by a few hundreds of metres, so there's small areas. So it's rapidly bursting out, then it shuts down, probably because the fluid pressure injection rate is not enough to sustain that further fracturing. It then sits there, then takes off later on. So these things turn out to be very common in the habanero, Cooper Basin injection experiments, not too common in some of the other experiments in Europe, but they're almost everywhere in the natural examples I've looked at. The final bit I want to bring you from the experiments is that there are very neat relationships which emerged quite some years ago now in the injection experiments to do with hydrocarbon recovery. And that is that the cumulative amount of energy released, this cumulative moment release, is directly proportional to the injected fluid volume. And here I've plotted some data from a number of experiments. Habanero is the red one up there, that's the Cooper Basin one. Below that is a Basel experiment, more data from Basel. And then one down here near Helsinki in Finland, which is a very, very careful injection experiment at 6 kilometres depth. And it was very slow injection, and they're trying to avoid as much seismicity as possible. So we see that the relationship between the cumulative moment release and the injected volume does vary by an order of magnitude, but for reasonable injection rates which match what we think we're getting in nature, we're up around about this sort of area in here. So we're going to use that sort of data to make some inferences. I'm going to throw you 3 areas briefly before we run out of time. One is a little earthquake sequence in California in 2015. We'll move on to look at a long-term history in Western Czechia, West Bohemia, near the village of Novi Kostel, where there's a lovely record coming out. And work I'm very busy on at the moment on Hakone caldera, which is near Mount Fuji in Japan. There's a lovely sequence from 1991 to 2020, which I'm working on. The Fillmore swarm's a little bit like that habanero experiment. It's a gently inclined thrust fault in Southern California. And again, injection starts here. We see the red stuff, and it progressively migrates with time. Okay, the blue ones are the youngest events. And notice it's migrating to the west, but it's not migrating to the east till very late in the sequence. So it's very anisotropic migration, and we want to understand what's causing this anisotropy of permeability enhancement. This thing produced nearly 1,500 events over a month or so. Biggest one's 2.9, so again, quite small. Depth is about 14 kilometres. It's down near the base of the Ventura Basin, probably in the basement underneath the Ventura Basin. Hypercentral area about 1.3 square kilometres, which is very similar to habanero. And again, it's dipping at about 26 degrees. Again, we see that characteristic migration of seismicity with time away from the inferred injection area. And as that anisotropy, it's migrating to the west much faster than it's migrating to the east. But see also there's bursts of seismicity, which is suggesting that the fluid injection is not constant. You get a burst, it probably runs out of fluid, got to build up the pressure again, then another burst, and so forth. And we see the bursts over here, magnitude time plot. There's 3 nice bursts, and again, if we look at the energy release, the cumulative moment, we see burst number 1 here, then a big burst through there, then it slows down, then it waits, then another subsidiary burst here. This third burst is probably redistribution of the fluid during the second burst. If we look at the cumulative moment and look at what's happening during injection or inferring injection, it looks like this earthquake swarm has been produced by about 25,000 cubic metres of fluid. Again, comparable to that habanero experiment in the Cooper Basin. The average flow rate is 50 litres per second or thereabouts, so think 180 to 200 tonnes per hour of fluid injecting there. We don't know where it's from. It's coming out of basement, underneath a very deep sedimentary basin. There's probably some sort of metamorphic reaction going on at depth. So that's just one swarm. There's not a lot of other swarms in that area, but where we can see the time series of these behaviours, is in Western Czechia. And there's a map over here. Here's the German border coming down through here. And a lot of the activity, most of the moment release, is in this blue area here near the village of Novi Kostel. And that's been firing away very happily since 1985 and 86 when the first big swarms were detected. The instrumentation in 85 wasn't good, but by about 1990, 1992, it became very good instrumentation and there's good records. What we see here, the swarm seismicity is actually distributed over 3,500 square kilometres. There's a historical record of seismicity that's longer than 500 years, so this stuff keeps repeating again and again. And what we see, and I'll show you in a minute, is a lot of CO2, carbon dioxide, coming out of the ground in this area. And there's a helium isotope signature, which is mantle-derived. So these fluids are coming from quite deep, and that's probably not a surprise because there are several small, tiny volcanic centres, basaltic scoria cones near the border with Germany, which were active in the Pleistocene maybe several 100,000 years ago. So there's probably some magma right down deep in the crust from the mantle, and that's cooking the crust, sending water, it's devolatilizing CO2, and that stuff's pouring out onto the surface. So it's a deep reservoir, and seismicity is very highly clustered in space and time. Interestingly, this Novi Kostel area has been firing off since 1985. It did so again late last year, and I haven't got that data yet. But since then, it's been very quiet, and activity has now moved up to Klingenthal in Germany, and it's been firing off furiously in the first few months of this year. So maybe the fluids actually migrated somewhere else now, because Novi Kostel didn't see any till 1985, so maybe it's just moved on. We've blocked that system up. So here's our time record. We've got swarms in the early 90s, 95, 97 is the first one that's well recorded, 2001, 2008, 11, 14, 13, 17, and I've got the last one there's 2021 to 2020, and there's one late last year, we haven't got the data for that yet. But what's going on there is a lot of CO2 is pouring out of the ground, and there's a little movie just here, I think we can play that. We got volume here. We seem to have lost our volume. There's very good bubbling effects originally. No, you just have to imagine the bubbling. It's very noisy. I don't know what volume of CO2 is pouring out, but it's over this very large area. So there's quite a lot of CO2 coming out, and that's consistent with mafic magma being in place deep in the crust. The strike length or strike extent of this fault system is about 10 kilometres. And we see seismicity over a depth of about 5 kilometres. I won't go into the details, but it's a network of faults which are variably linked. If we go in detail, here's a north-south section. We see seismicity, the shallowest is about 6 kilometres deep, down to about 10 or 11 kilometres deep. And there's a clear migration of seismicity with time. I'll show you that in a moment. And here is a map view. We see one fault system there, then it steps across in echelon to another fault system there. There's a lot of complexity. I've just given you 3 sections here. And this data was just recently provided by Thomas Fischer at Charles University in Prague. They've just reprocessed the early data. And we're seeing really detailed geometry. We see a fault here which is dipping steeply to the right, then it goes into a fault which is dipping steeply to the left, and there's another one. We've got sound maybe. No. Okay, next. This is just a brief cartoon. Don't take any, sorry, not cartoon, but data set. This is the 97 swarm, a very tiny one. The 85-86 swarm was largely in this area through here. The location's not good because there are only about 2 seismometers in the area, so location is very poor. But by 2000, when the next swarm occurred, we had seismicity start here at depth of 10 kilometres. It migrated up, went anti-clockwise and died out down there. Then there was a little blip of activity up there. In 2008, swarm occupied the same area, but expanded to a bit larger volume. 2011 started where the other one left off and migrated depth to the north, a little bit going up. A little bit of chatter going on in 2013. 2014 was another big swarm which is linking 2 faults. There are 2 faults and there's a step over between the 2 of them, and a lot of seismicity was located in that step over. 2017, another swarm way further north. 2018, a complicated system of activity filling in the space between 2014 and 2018. 2021, it's migrated back further north again to where the 2017 swarm was, And last year's swarm was a little bit further north, and then it seems to have stopped. The 2021 swarm is rather interesting. It's on a steep structure, or a series of structures, and the activity started down here. Activity lasted for quite a long time, about 150 days. It started in this red stuff here. It then moved in another phase to a lot of small events in here. Then all of a sudden it jumped up to here and migrated rapidly downwards. So we're seeing fluid migration directions are very complex in these systems. And here's the three phases of activity plotted as depth. So you've got really deep activity, then more deep activity, and then when you go shallow, then rapidly migrate to depth, and then it starts migrating up again. So complex hydrology indeed. Those three phases, we can do the calculations of injected volume and flow rate. We're talking about, in phase 1 and 2, about 20,000 cubic metres of fluid. But phase 3, where a lot of the moment release occurs, is about 70,000 cubic metres of fluid injected at rates up to 300 litres per second. So we're talking about 400 or 500 tonnes per hour of fluid injecting into that system over quite a short time. Haddon is really interesting because it's a really nice subvolcanic system. There's a rather nice caldera shown as digital terrain model over there. Mount Fuji, by the way, is just there, it's next to it. Mount Fuji is a much younger structure. This is a mature volcano. Another mountain in there is Mount Ashitaka. So this is a now dominantly andesitic caldera complex with some andesite domes in the middle. It has an eruptive history of about 400,000 years, and the last really significant magmatic activity was 3,000 years ago. But it looks like it's been fluid active for a long time. There's a lot of alteration. There's a very active geothermal system, a little bit of geysering, mud pools. There's just stuff pouring out of the ground everywhere. But interestingly, for one of these volcanic systems, it's seismically exceptionally active, and I'll show you that in a minute. And so this becomes an analogue for intrusion-related subvolcanic hydrothermal ore systems. Haddon's been well instrumented since 1995. They've got a beautiful network of seismometers around the caldera, which occasionally get wiped out by typhoons, but there we go. One of the biggest swarms is 2011, this one up here, which is not really an ejection-driven swarm. It was triggered an hour or so after the huge tsunamigenic event in 2011 in Tohoku, off Tohoku. Those seismic waves came through Haddon and just unhinged a whole bunch of faults. So some really big activity fired up. It was very quick, but very high energy. The database, which I've got, has nearly 29,000 events. The biggest event, 4.9, during that 2011 swarm sequence, but typically they stay less than about 4. And on the diagram on the bottom right, you can see the blips, the steps are when the major swarms occurred. We won't go into detail of much of those. But there's a map of these nearly 29,000 events. There's a map view here. There's a very dense zone of seismicity, which I call the eastern seismic zone. You can't resolve a lot of structure in there. There are lots of little faults at the fine scale, but at this scale we can't resolve them. In the western seismic zone, we can actually image a whole bunch of detailed faults. We can see some of them in here, but it's like a cloud. It's a bit fuzzy, but I'll show you more in a moment. So here's an animation which Drew Whitehouse from National Computation Infrastructure has been working on for me. And this is a digital elevation model of Haddon looking towards the northwest. And we'll play that. Maybe it'll play. And what we're going to do is zoom in on that, take the surface topography away and look at the volcanic generated swarm system, which is hydrothermal. There it is underneath. The scale on this is the length is about 10 or 12 kilometres and the depth is about 8 kilometres in there. Okay? We're going to rotate this database and you can see the seismicity illuminating faults. They're often blade-like fault zones, but there's also a lot of diffuse seismicity. And you'll see the seismicity go off, counted by the year counter down the bottom. Lots of little swarms. The first significant swarm's 2001. You'll see that in 2001. Click off, there it goes. It's lighting up a large part of the area. Watch again for about 2006, 2007 to 9. There'll be a whole series of swarms fire off. In that orientation, you can see these nice planar faults illuminated by the seismicity. 2009, that one goes off beautifully. Then 2011 is when the tsunami earthquake went off. And the really big event is 2015 coming up when the most seismic energy release in this system. So it shows you very nicely we've got episodic pulses of fluid being fed into the system, driving seismicity. Here's one of those fault zones which were activated in 2015. I call it W1 fault zone. We've got a nice map of seismicity here. It started over here in the west. It migrated systematically around through this area through here, and then ended in the blue zone up through there. The map view, without the coloured circles, is just the hypercentre locations, really illuminates we've got a mix of these north-northwest trending structures and this west-northwest trending structures as well. So there's two what we call conjugate sets of faults activated. The next one is an animation, which again Drew just produced for me in the last week or two. We're looking down on it. What we'll do is we'll rotate that so we're looking towards the north eventually. You can see the north arrow in the bottom. You can see some nice faults illuminated by seismicity. We'll spin it around so you can actually see the 3D geometry of this structure. And this red dot is the very first event we're going to see go off in a minute. So we'll swing that around till we get looking north again. You can see the various faults illuminated by the seismicity. What we'll see is the seismicity starts, the counter will start down the bottom. We'll start over here in the far left. There it goes. And see it progressively migrates towards this zone in here. And watch this zone, particularly at about day 7 or so. So there's a lot of snap, crackle, pop going on. Then at day 7, boom, massive amount of seismic energy release, twinkling of the stars as they go out, and then about day 10 or so, we have a second burst of activity. And finally, at about day 15, the end of it is really this zone up here is lit up again. It was lit up early, but it lights up again about day 15. There she blows. So it's really interesting. We can actually see these things migrate systematically. We quantify that if we want to. Oh, won't let me do it. We've got to wait till we get to 20. Okay, there we go. So again, here's that same data plotted as a function of depth over time. Here's that last event at day 15. It's one of those migratory seismicity bursts. Early in the system, it went deep from about -1 down to 3.5 kilometres, but not much seismic energy release. We had a big burst of energy release then, and that was when most fluid injection is inferred to occur, and we're talking about something like 55,000 cubic metres of fluid. 1,200 litres per second. That's a lot of fluid going in, but only for a very short time. Oops. It says wait. There we go. So what are the implications of this for ore deposits? Swarms are the characteristic behaviour of the crust when fluid is injected into low permeability rock masses. These provide a contemporary analogue for the formation of many overpressured fault-controlled ore deposits like orogenic gold, some intrusion-related systems, iron oxide, copper, gold and so forth. The close spacing of the earthquake nucleation points, the hypercentres, gives us really high-resolution images of the architecture of activated segments of faults and are giving us some new understandings of how fluids migrate through faults. They're not just going upwards, they're going downwards, they're diving off to the left or right, they're doing complex stuff and they change with successive swarms. The timescales of rupture sequences are giving us some insights about the timescales of episodic flow, essentially the hydrology of these systems, and it's very episodic and very fast migration at times, and also reaction and order precision. It's not a simple steady-state flow system. It's very episodic. Fluid pressures are changing on timescales of rupture propagation. That is less than a second we're getting fluids migrating. And we're also getting good understanding of the cumulative moment release, the average slip rates and so forth, which constrains rupture sizes, fluid volumes, injection rates and durations of ore formation. It's slowed down on me. It says I'm too slow. There are some implications for this. So we've got this data now. We know what the rupture diameters are that form these deposits. The gold deposits, for example, they range from less than a metre up to the biggest ones are probably only 1,000 metres, but most are much smaller than that. Total fault slips of 100 metres in these systems must accumulate by thousands of earthquake swarms, so each swarm having thousands to tens of thousands of events. So we're looking at tens of millions of microseismic slip events to to produce these structures. Each swarm involves 1,000 to 10,000 small ruptures over days to months, or in some cases, such as some of the California swarms, up to 2 or 3 years. They're very slowly evolving systems. And we have this diffusion-like migration of seismicity, which tells us a lot about the rate of permeability enhancement, the rate of fluid migration, but importantly, very strongly episodic flow regimes. The timescales are vast, so we deal with swarm recurrence of the order of decades, maybe centuries. So flow is switching on during a swarm, it's switching off between swarms, so they're more often than not inactive than they are active. Swarms themselves last from a day to maybe a year or a couple of years in some cases. We have these bursts of activity within swarms which last, in some cases, a day or so, but within those we also have these migratory bursts which last for an hour or so. So you've got this punctuated fluid flow, bang, 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 going on. Down to the timescale of individual ruptures. The small ones propagate for perhaps a few milliseconds. The biggest ones, the 1,000-metre ones, are migrating for maybe a second. And as those ruptures propagate, they're opening, dilating, causing the fluid pressure to drop fantastically. And fluids could be moving at rates of tens of metres per second in that environment. So going back to where we got in the very start, that there are many, many more ruptures at the small end of the spectrum than there are at the large end of the spectrum. So if we have, for example, one rupture that's magnitude 3, rupture donor of about 360 metres or so, we're going to have 1,000 magnitude 0 ruptures in there. So most of the slip events which are produced in these deposits are very small events. We've got fluid pressure fluctuations going. We pressurise the system. If we're at low differential stress, we can then limit that pressure build-up by the opening of these hydraulic fractures, the extension fractures, until the shear stress equals the shear strength, then bang, the fault ruptures and away we go. At high differential stress, we pressurise and we go straight to shear failure, the fault slip, the earthquake-producing event. So we've got this sequence, fluid pressurisation, where fluid is injected into the fault zone. Here's our rupture front somewhere here. Fluid is injecting into the rock, reacting with the rock to produce gold deposits which are disseminated. Maybe gold's depositing within the extension fractures in there. But the moment that rupture propagates, and might propagate for maybe 0.5 of a second, it dilates. What happens? As it dilates, the fluid pressure drops dramatically. There's a reorganisation of the hydrology, that fluids are now flowing in from the sidewalls as well as from the upstream reservoir, which is feeding the whole system. So we get this back mixing, and then the whole system's flush with new things. And we do this thousands and thousands of times during each event. This is just highlighting the fluid pressure cycles we might see. So here's a plot of some migrating seismicity. The first event's here, they're all numbered. Let's think about the fluid pressure variation at A. At A, we don't see any effect from 1, 2, 3, 4 or 5 or 6 because they're not hydraulically connected to A. But then the fluid comes along from those ruptures and builds up the fluid pressure. It then fails. Okay, we have a massive stress drop, fluid pressure drop. Then the seismicity starts migrating further away, and there's no more events rupturing at A until we get our tier to event 18, which occurs in A again. That'll drop the fluid pressure there. But all these other events are now hydraulically connected to that area, so we'll see all these ruptures are having an effect on the fluid pressure. So there are a large number of fluid pressure fluctuations, in fact, thousands of fluid pressure cycles at each location during each swarm. So it's a very dynamic ore deposition environment. Timescales, I won't go into detail in this one, but if we can do some sums for the average length of a fault, the average slip per swarm, it tells us that the net slip in one of these systems can accumulate in 10,000 to 100,000 years. That's how long it takes to produce one of these gold deposits. Only 10,000 or so years. 100,000 years maybe, but not millions of years. They're very fast things. We can also use the relationship between injected volume and cumulative moment release to pull out some data on the fluid volumes associated with orogenesis. And you do all the sums, it comes out as you need basically a Sydney harbour to produce a gold deposit of 50 tonnes of gold. That's not so different from what the geochemists would tell us. It requires the fluid to have up to 0.15 ppm gold. That seems rather high to me, and John might have a comment to say about that later, but That's about the upper limit of gold solubility in relevant fluids, but it's high. They may be colloidal nanoparticles even in that system. So where does this bring us at the end? So these fault-related deposits, and the example I've used is the orogenic gold, form in active fault zones, not dead fault zones. We don't create a structure, then use it later. No, we create it with the fluid pressure. There's large volumes of overpressured water CO2 fluids. The deep injection experiments tell us that injection of fluids drives migrating seismicity, and importantly, the cumulative energy release is directly proportional to the injected fluid volume. And that's powerful for understanding what's going on in the natural systems. It provides a tool to quantitatively assess the fluid volumes associated with both natural, contemporary fluid-driven swarms, and also the formation of ancient deposits in old terrains like the Archean of Western Australia or Canada or elsewhere. Importantly, the natural-driven swarms and the injection experiments, the really deep ones into crystalline basement rocks, provide an amazing analogue which we can use to understand these fault-related ore systems, with its insights about fluid volumes, rate of flow, timescales of deposit formation, the complex dynamics of fluid migration in these systems and reaction, which we're only just starting to think about. And it's also providing a lot of insights about pathways of fluid flow, which we can't get from looking at the preserved rocks very easily. Are there some broader implications? I'll just touch on it in the last few minutes of the talk. There's these things called enhanced geothermal systems where people drill deep holes, as in the Habanero Cooper Basin experiments. You drill into deep rocks, pressurise it, make it fail, and then mine the heat from those rocks. But most of those experiments failed, and they failed why? Because in natural swarms and in the preserved deposits, we see that once you make a fault, that fault gets repeatedly reactivated. You can't expand the volume of fractured rock, which means you can only strip heat out of that very narrow volume of that one fault. So we've got to learn, if we want to get heat out of deep hot rocks, how to pervasively fracture the rock mass. In places like Hakone might be able to tell us something about that, because there we have one zone in the eastern seismic zone which is very pervasively fractured, and heat's pouring out of that at the moment naturally. For deep sequestration technologies, there are some cautions I have. People are talking a lot about, oh yeah, we can get rid of CO2 by pumping it into the ground. The problem with that is that if you pump large volumes of fluid into the ground, what's happening to the fluid pressure? It's increasing. You set out fluid pressure gradients, those fluids migrate. And I'm not such a hydrologist that I know where they migrate to, but there's the inherent danger that you'll rupture the boundaries of the reservoir and that fluid will leak out. So you've actually got to do a solid state sequestration. You've got to produce minerals which lock that CO2 up. Liquid CO2 sequestration is doomed to failure. And the final message here is that pressurised fluids self-generate their own permeability. They crack the rock. So even from the deep mantle, fluids work their way out by cracking rocks at anything from micro scale up to macro scale. And just the final one is a photograph from a pavement on the Roosie Fault in Cornwall, which I've done a bit of work on. It's very pervasively fractured, and it's a very nice example of fluids cracking the rock to find their way out. In this case, they're trying to get shallower and shallower. There are some acknowledgements. My minerals industry colleagues have been amazing in giving me access, for me and my students and others, to various deposits in various parts of Australia, PNG and Victoria. There's been a lot of logistical and financial support from the minerals industry, which has helped me enormously. ARC, through Discovery Linkage and Centre of Excellence grants, has been amazing. Thomas Fisher at Charles University in Prague, Yaha Yukitaki, who's at Earthquake Research Institute in Tokyo, have been amazing in providing high precision catalogues for me to play with. The European Plate Observing System has given catalogues for the injection experiments around the world. And I also thank again the many honours, graduate students and postdocs who have given me years and years and years of enjoyment working on ore deposits and fault earthquake mechanics projects. And finally, I want to acknowledge the IT support. Brian Harold, who couldn't be here tonight because he got our RSV the other day, gave early support in how to handle these complex earthquake catalogues. Rhys Hawkins, who got me into 3D imaging of these things initially. Now Drew Whitehouse at National Computation Infrastructure is helping with generating these lovely, gorgeous animations. Thank you very much.
You can stay
Okay.
Well, thank you very much, Stephen. Fascinating talk. I'll never look at my marble bench tops in the same way again. Such a fantastically rich problem. I think an inspiration that how fundamental science in such a rich natural phenomena can lead to new understandings, but so important for the prosperity of Australia. And I can see a lot of young geoscientists here. I assume you're geoscientists. It's really a fantastic area, so thank you, Stephen. I'll open the floor up to questions from the audience, and those of you online, you can submit questions via the code on your screen. Please just raise your hand. There'll be a roaming microphone, so if you just wait for a microphone.
Hi, Steve. Thanks a lot. Given that you've quantified the volume of fluid that you're talking about in these systems, and there's been a long-standing debate about the origin of fluids in orogenic gold systems, presumably you've then thought about how much volume of rock, metamorphic rock, would be required to extract that much fluid to get into these systems, and what do you come up with when you do those sort of calculations?
You don't need a lot. It's of the order of 10 kilometres by 10 kilometres by maybe 5 kilometres. The real trick in that is we don't yet understand how you actually get that fluid from the grain scale in that metamorphosing rock into the fault zones, and that's a real thorny problem. Presumably it's grain scale migration initially, then there must be fracture networks, a little bit like a dendritic drainage system, but we don't really understand it. We need to get into that mid to deep crustal environment and really try and interrogate the rock about what those pathways are.
Question online, I believe.
Yes,
Wendy?
that's right. We've got a few questions online. I'm not sure whether you can answer this, but Gavin from Cairns has asked, could you go into a bit more depth on why the Newcastle earthquake happened, yet has not reoccurred?
Maybe. It occurred because the crust is being loaded by the collision out in New Zealand. So the Pacific plate is colliding with the Australian plate, which goes out as far as the west coast of New Zealand. That's transmitting stress through the upper crust and the mantle lithosphere to Australia. And it just so happened that that point in time, at that place, the stress which is being imposed on the rock became equal with the strength of that rock, and it failed. What's fascinating with that is that there were no aftershocks that we know of. That's really rare, and we don't understand what's going on there. But what is also interesting is some people at Newcastle were doing offshore seismic studies mapping the recent sediments on the seafloor. And offshore from Newcastle there's a wonderful scarp in those sediments, and that's almost certainly where that fault comes up and meets the seafloor, and it's clearly been active for hundreds of thousands of years, but the plate stressing rate in that area is very slow, so don't expect a recurrence for a long time. Might happen tomorrow, but statistically it's going to be a long time.
Question at the back.
Thanks, Steve. Really interesting stuff. The idea of the veins or the fluids only moving along the faults when they're active, and also the veins sort of forming in repeated openings and closings, so cracking, sealing. How do you think something like a magma or a dike formation moves along these structures? Often dikes are quite large. Zonation internally looks like it's almost one intrusion of magma along it. But do you see them sort of forming in the same episodic way, or a single pulse? If you've got something of much higher viscosity like a magma, perhaps?
Good question. If you go down a place like Binji Point, where the students often go on field trips, you can see tertiary basalt dikes down there, which are clearly multiple injections of magma. You see the textures change, but they're not the fine scale that we see in crack-seal veins, which are sort of 50 to 100 microns. Down there, a dike that wide might have 3 increments in it. But the perfect example is to go and look what's happening in Iceland now. There we've got, I forget when the first big eruption occurred, sometime during last year, but about every 3 months it goes off again. and it seems to be inflating the same conduit. So magmas are a bit like fluids, they're just more viscous. They do it a little bit differently, but they certainly generate earthquakes. But the earthquakes we're seeing in Iceland are not due to shear rupture propagation along the conduit. In the gold deposits, it's conduit. But in Iceland and wherever you've got a dike in place, it's the magma pressure. It pushes the rock aside, it stresses the rock. Little faults are firing off all over the place, particularly around the propagating front of that dike. And this was mapped really nicely way back in the, I think it was early 2000s, late 90s. There was an amazing dike swarm off the coast of Japan, Miyakijima. And that produced a whole swarm of magnitude 6 earthquakes and millions of smaller ones. It was quite incredible. But most of the earthquakes were not on the dike itself, but ahead of it or off to the side of it.
Question up here, Kira, just, if you just raise your hand again to, yeah, thank you.
So you know that beautiful picture you had just a second ago where there was like a kilogram of gold and some veins there?
Yeah.
If these swarms are moving around all the time and we only have a small amount of gold dissolved in the fluids, how do we build something like that so incredibly huge?
I put that up to annoy myself mainly. Tell me that I don't know why we have such rich gold. So I can give you an example at Fosterville where we're working at the moment. There I showed you the sample which has grades of 1 kilogram per tonne, nowhere near as big as that Kambalda one. But there it looks like we formed most of the vein system, maybe 90% of the vein system, and produced low-grade gold and lots of disseminated gold in the wall rock around it. But the microstructural relationships at the thin section scale say the bonanza grade gold has come in a very late event where quartz has been dissolved, not deposited, producing pore structures, and the gold is then depositing in those pore structures on top of a new generation of quartz. The content of gold in that fluid must be humongous. And I don't know if it's nanoparticles or what, but it's got to be above the chemically defined solubility of gold in fluids at those conditions. So it must be incredibly supersaturated fluid. And you can do that if you think of the velocities at which these fluids move. They're migrating hundreds of metres per day. So you might pull it from 12 kilometres to 6 kilometres very, very quickly. And it's probably going to be very hot. Pressure's dropping really fast, temperature's dropping really fast. Totally supersaturated.
And we'll have one last question because we are slightly running over time.
So you know how to do this for yourself. You could make your own gold mine, couldn't you? The volumes of fluids are within achievable ends. Just find some gold deposited around and pump it up and concentrate it for yourself.
Pump seawater through.
Well, yeah.
But they're going to be parts per billion, if that.
No, you're going to find a way to concentrate this, Steve.
Yeah, well, it's something for you to do, Richard.
So an interesting endeavour going forward. I've got lots of questions, but I'll save them for later for refreshments. So again, thank you for your questions. I'd like you to please join me in thanking Stephen again for a fantastic lecture. Congratulations. And thank you to all of you for attending, for your active participation, both online and here. For those of you who are here, please join us in the Jaeger room for refreshments. So that concludes the event. So thank you very much and good evening.